Anyway, so I will talk about, so the talk today will be, sorry about that, will be about conformal field theory techniques to study scattering amplitudes in theories of gravity and in particular in M theory. And this is based on work in collaboration with Shai Chester and Himanshu Raj and Chinan Zhou as well. And I will try to go slowly and be very pedagogical. This has the risk of maybe taking me slightly longer than otherwise, and maybe some people will get bored, but I wanted everyone to understand what the problem to be addressed is. And please feel free to stop me at any time and ask me any number of questions. So a scattering amplitude is basically the probability, in this case a 4-point scattering amplitude, is the probability that if you have two particles colliding with momenta P1 and P2, they result into two other particles with momenta P3 and P4. This scattering amplitude, here denoted with A, can depend on many things. It depends on which particles you are scattering, their masses, charges, etc. It can depend also on the parameters of your theory, here denoted with G, collectively with G. And it also depends on the momenta of the particles being scattered through the three Mandelstam variables, S, T, and U, which are these combinations of the momenta P1, P2, P3, P4. Now, one may ask, why do we need to study scattering amplitudes? And there is actually a lot of motivations. So one reason is that they can teach us much about the symmetries of a theory. And over the last few years, we have been learning a lot by studying scattering amplitudes, let's say in n equals 4 super-Yang-Mills. Then they can also uncover beautiful mathematical structures that if you just look at the Lagrangian of a theory, all these structures may not be obvious, but if you go and study scattering amplitudes, then you can discover things about the theory that are not very clear otherwise. But of course, as a physicist, we should be interested because they actually allow, they are the observables that allow to test the predictions of our theory, okay? So we have a theory, we compute a scattering amplitude, we go and measure in nature what these amplitudes are, and either we agree or disagree with nature. So we need to study scattering amplitudes for a variety of reasons. Now, a theory that we would like to understand is just the Einstein theory of pure gravity, general relativity. So we could study scattering amplitudes in pure gravity. Pure gravity is described by the usual Einstein-Hilbert-Lagrangian. And in this Lagrangian, we can consider a scattering process. So we consider perturbations around the flat space metric. We write down like an effective action for these perturbations, whatever, and we study the scattering of gravitons in this theory. What happens, it is well known from computations by Toft and others many, many years ago, is that pure gravity, general relativity, suffers from ultraviolet divergences. The gravitons can get, in a way, too close to each other, and it turns out that pure gravity is not a consistent quantum theory of gravity. You can absorb these UV divergences at one loop, but at two loops, that's not possible. So this is not a consistent theory of gravity. Because of that, we have to study completions of general relativity, of pure gravity. And one such example is, of course, string theory. But today, we will try to understand scattering amplitudes in M theory. Now, M theory, I will not say much about M theory because we don't know a lot about M theory. And I think it is fair to say that we don't have a non-perturbative understanding of M theory. So what we will focus on, we will focus on perturbative M theory. And a definition of perturbative M theory is that it is given by 11-dimensional supergravity plus higher derivatives correction, okay? So this is the effective action of M theory. The first term corresponds to 11-dimensional supergravity, and then we have a tower of higher derivative corrections that become important at high energies. So I would like to make a few comments about this effective action. So first, notice that higher derivative terms carry powers of this length L11, which is the 11-dimensional Planck length. This is the only parameter that we have in the theory, because M theory has no dimensionless coupling constants. In a string theory, we would have alpha prime as well, but here we have just this L11. Now, it turns out that one can show that the first two corrections, which are diff2 r to the 4 and diff4 r to the 4, they can be shown to be absent. The coefficients of alpha and beta, the coefficients in front of r to the 4 and d6 r to the 4, are actually known. You can dimensionally reduce this in one dimension to type 2A string theory and compare this with the known results in a string theory. But already from this term here on, nothing is known. So beyond what I wrote, nothing is actually known. So all these coefficients are actually unknown. So we don't know either if they are 0 or not, for instance.
So the fact that the D2 r to the 4 and D4 r to the 4 are 0, that follows from supersymmetric?
That's absolutely correct. So to fix the first 4, that's absolutely correct. So they are protected by supersymmetry. And so there are two computations. So one is like whether supersymmetry protects them. And also you can reduce this in one dimension and you can compare them to results in type 2A string theory, where also these things are protected by supersymmetry. So it is basically, so they are protected by supersymmetry.
And is there some sense in which these terms are sort of integral over half of superspace, while the unknown term is integral over all of superspace?
Probably, actually, yes. So there has been papers on this by Hook and collaborators, the Hook, I think, and collaborators. And yeah, that may be correct, but I don't want to lie to you. So I should revise this computation.
Thank you.
Now, there is a slightly better way, a nice way to study these on-shell amplitudes. Sorry, these effective actions by studying some on-shell quantity, and the shell quantity here is the amplitude of the scattering of gravitons. So we can consider the on-shell scattering of 11-dimensional gravitons, and the 4-point amplitude of gravitons has a structure that mimics the structure of the effective action. So in 11 dimensions, gravitons have some momenta and some polarization vectors, like in any other kind of dimensions. And what happens is that, again, because of supersymmetry, one can show that all polarization dependence can be put inside a universal factor denoted with k hat. Then we have an expansion in powers of the length L11, and we interpret this expansion as a momentum expansion. And this is the answer, of course, in flat space. Now, the first term in this momentum expansion corresponds to the supergravity approximation. It's just 1 over STU. The second one corresponds to the vertex r to the 4 and is proportional to 1, just a 1 here. Then we jump to this 6 r to the 6, and we have this cubic term in the Mandelstam variables, ST and U, plus ... And about these dots, I would like to say two things. So first is that the coefficients of higher polynomials in ST and U are not known. So this is the same ignorance as the ignorance here for this term d to the 8 r to the 4. And in addition, we have some loop corrections which are known that arise from the square of these supergravity corrections here, but they are very complicated non-analytic functions of ST and U. For instance, the first one here is proportional to L11 to the 9 here inside, and is equal to the 11-dimensional box function. And as you see, I just took a little bit, is some complicated non-analytic function of the Mandelstam variables ST and U. Now, so even in flat space, only these three terms are known, and only the first loop supergravity bit is known. So not much is known about this amplitude, even in flat space. And of course, curved space is completely terra incognita, and we know nothing about it. So the idea is to try to learn about these terms in the 11-dimensional graviton scattering, and especially to try to understand what we get in curved space. And for that, we will develop an alternative approach. So any questions before I proceed?
Fernando, would unitarity be sufficient to fix the sign of alpha and beta?
No. So that's a very good question. So here, indeed, here there are two kinds of terms. There is the non-analytic terms and the analytic terms. So with unitarity, we can fix the discontinuities. So we can actually fix the non-analytic terms. While here, for alpha and beta, these are fixed in terms of these coefficients, alpha and beta. So at the end of the day, one does a comparison with the answer in string theory.
Okay.
Fernando,
So yes.
So how this k hat function, does it depend on L11, or it's just an overall dependence?
Oh, sorry. No. It's an overall dependence. So I will tell a little bit about it later on, but it's just a function of the momenta, P1, P2, P3, P4, and the polarization vectors, zeta 1, zeta 2, zeta 3, zeta 4. It's some complicated contraction of all these tensors, but it doesn't depend on L11.
And how do we know that the higher terms cannot depend on polarization in a more interesting way?
Because what happens is that so what you are considering here is the super multiplet of the graviton in 11 dimensions. And it follows from word identities that once one component is fixed, all other components are fixed in terms of one of these components. So basically what this is telling you is that there is a unique function of ST and U, which is non-trivial, and all the rest, so all the other components of the super multiplet are fixed in terms of this single non-trivial function.
But that argument would hold for when the polarization is some R-symmetry polarization, right? Or it's also for this polarization?
So I think in 11 dimensions, it works for any polarization. The same happens in 10 dimensions, by the way. So you can show that the graviton state has 256 different components, the supergraviton multiplet. And the 4-point function of any of these 4 components follows from any single component. So they are all related to each other by supersymmetry.
One more question.
Yes.
This loop pieces, a priori, do we know anything about their analytic structure? For example, the term that you wrote, these powers and the logs were to be expected in some way?
Yes, actually. So I am not writing the full answer. I have the full answer, but it was a bit too complicated. But basically, the first loop, so of course, all the loops we don't know, but the simplest loop arises, so it is equal to the 11-dimensional box function. So there is a function which is called the box function. In 4 dimensions, this box function is relatively simple. And in 11 dimensions, it's not that simple, but it can be computed. And this is just a little bit of the answer. But yes, the answer is fully known. But this is the first loop correction. It's a loop correction that arises from the square. I will be much more explicit later on. So I will give you an integral representation for this answer here.
But what do you mean full answer?
Sorry.
What do you...
So of course, loop corrections, in principle, you can have like an infinite amount of diagrams.
Right.
And it's just the first diagrams, the ones that are known.
Okay, I see.
I will be more explicit later on.
Okay, thank you.
Yeah, I have a related question.
Yes.
And in principle, are all the loop corrections fixed by the polynomial terms?
Yes, that's a great question. Indeed. So what happens is that you can develop a unitarity method, and you can compute a given loop order by cutting diagrams and putting diagrams together at the previous order. But what happens is that at each order, you will have polynomial ambiguities.
Okay.
And in order to fix these polynomial ambiguities, this in a way is the non-trivial information that M-theory should tell us. So all the non-analytic piece, all the discontinuity piece follows from previous orders. But at each order, there are these analytic pieces. And in order to fix these analytic pieces, that's hard. And that's the reason why we would need to understand M-theory in a perturbative expansion. In another way, another way of putting it is that we will have terms like this alpha, beta, etc., but with higher powers of L11. And those cannot be fixed from previous orders.
Okay, thank you very much.
Right, but just to make sure I understood, suppose the analytic part was completely given to you, then the non-analytic part, I mean, to all orders in L11,
Yes.
then the non-analytic part just follows.
That's right. However, of course, when you are computing, yes, yeah, in a way, yes. You would have to be a little bit careful, because when you have, let's say, divergent diagrams, you always have these ambiguities. But if someone tells you what this analytic part is, then the non-analytic part does follow, yes.
Thank you.
So we would like to understand this structure, and in particular to extend this structure to curve space. And our tool, we will need a completely new approach. And our approach will be, so we will return, by the way, thank you so much for all these questions. Keep asking them, because we will try to answer them from a different point of view towards the end of the talk. So our workhorse to attack this problem now in curve space will be the EDS-CFT duality, but now for M-theory. So the EDS-CFT duality in this context tells us that M-theory on EDS7 cross S4 is dual to a 6-dimensional super-conformal field theory living in the boundary of EDS7. And this theory happens to be the 6-dimensional 2,0 theory of type A(n-1). And it is the word volume conformal field theory that lives on M5 branes in flat space. And it is the maximally super-symmetric theory in 6 dimensions. And this theory has a central charge, and it turns out that this central charge goes more or less like n cubed, where n is the number of 5 branes, M5 branes. Now, the EDS-CFT duality provides us also with a dictionary between the parameters on both sides. Recall that I told you that in M-theory, there is not dimensionless coupling, but as soon as you put the theory on EDS7 cross S4, there is a new length, which is the radius of EDS, which is related to the radius of the S4. So now we can form a dimensionless parameter, which is L EDS over L11, the 11-dimensional Planck length. And this dictionary relates the 9th power of that parameter to the central charge of the CFT. So we have this duality, and the duality has this dictionary over here. Let's try to fill a bit more precisely the entries on this dictionary. So the duality, ADS-CFT duality, also give us a way to define M-theory amplitudes on ADS7 cross S4. ADS7 is like a box, so it's not so clear how to define amplitudes. But ADS-CFT duality tell us that we should interpret, so the way to define an M-theory amplitude on ADS7 cross S4 is through correlators of local operators in the theory that lives in the boundary, which in this case is this 6-dimensional 2,0 theory, okay? So we will map the amplitude we want to study, and now we will convert that into a problem of studying correlators in this 6D 2,0 theory. Is that okay? Then let's make the dictionary slightly more precise. Sorry. So because of the dictionary here, this entry of the dictionary, notice that the momentum space, the momentum expansion, which was an expansion in powers of L11, maps to a 1/c expansion for the correlators in the 6D 2,0 theory. On the other hand, the graviton on ADS maps to O2, which is a protected scalar operator of dimension 4 in the stress tensor multiplet in the 2,0 theory. While, since we have an S4, we also have a tower of Kaluza-Klein modes on the S4, and this map to a tower of scalar operators, which I will denote by OK, of dimension delta equals to 2K. So if we want to study graviton, scattering of gravitons in M theory, the problem we have to study, the equivalent problem, is to study these correlators, OK1, OK2, OK3, OK4, in the 6D 2,0 theory in a 1/c expansion where C is the central charge. Is that okay? So now the problem we want to study is this problem. And as I try to argue, that is equivalent to study M-theory amplitudes in a momentum expansion. Is it clear? Okay, so did everyone understood the motivation? It should be more or less clear, but it will get a bit more technical now.
Fernando, sorry,
yes.
This one of the expansion is slightly different from momentum over L11 expansion.
Yeah, so there is, so I guess what you can see here is that if L11 is large, the central charge is small, okay? So an expansion in positive powers of L11 goes to an expansion of powers, of inverse powers of the central charge. But what will happen, as you will see in this dictionary, is that the powers of the central charge may be fractional. Mm-hmm. Okay, and we will have that phenomenon. That will happen.
No, but I guess you would also have to worry about momentum scaling, right?
Oh yes, yes. So yes. So let me. Yes, I will answer that towards the end of the talk.
Okay.
So for the moment, let's say that you work in units in which this L is equal to 1, let's say, and then the expansion in powers of L11 is equivalent to this. So you can measure L11 in units of LADS.
Thanks.
Great. So now let's. Yes, sorry.
A question. So is there a limit on K with respect to N, and would you be considering like K much smaller than N?
Yes, absolutely. Absolutely. So here, yes, that's an excellent question. So here I will consider K1, K2, K3, and K4 finite. And in particular, they will be much smaller than N. Yes.
But is there an absolute limit, like even at finite N? And how?
So I will work in a 1/c expansion.
Okay.
And I wouldn't know how to work at finite C. But I will mention, actually, I will mention, thank you so much. So I will mention some things about finite C towards the end of the talk. But for the moment, we will work in a 1 over C expansion. So C is much bigger than any other parameter, and in particular, it's much larger than this case.
Okay, thank you.
Great. So
maybe I can make a quick comment here.
yes.
The partition function over 1/8 BPS states in this theory has been counted. And so you see trace relation kind of things occurring when K becomes N.
Yeah.
If you want to see where the first trace relation is, it's at N. And
fantastic. Yes, so here K will be much smaller than N. So yeah, that's a very good point. So indeed, so we won't have, so these trace relations, we won't see them. Yeah, but very good. Great. So let's try to talk just one slide about the structure of correlators in the 6D 2,0 theory, just the kinematics. So the 6D 2,0 theory is the maximally supersymmetric theory in 6 dimensions. And the superconformal algebra is denoted OSP 8*/4. The name doesn't matter too much, but the bosonic subalgebra is SO6 2,2, which is the conformal symmetry in 6 dimensions. And then we also have the R symmetry, which in this case is SO5. We will look at the half BPS operators, and the half BPS operators in this theory transform in the symmetric traceless representation of SO5. So we have operators O evaluated at a point X in 6 dimensions, and they have these K indices where each of them run from 1 to 5. And we want these indices to transform in the symmetric traceless representation. Now, it is very convenient to introduce a null vector Y, we will come back to this null vector, and contract all these free indices Y with the indices of the null vector Y. So we will define a vector, an operator, sorry, OK, which is a function at a point in a space-time, and also contains this null vector Y defined in this way. And then we can study the 4-point function of 4 of these guys. And just for simplicity for the formulas, I am putting K1 equals to K2 equals to K3 equals to K4. I am denoting all of them by K. But all what I will say is true actually also for generic K1, K2, K3, K4. But in this simple case, it turns out that you can extract a common prefactor and you can write the full correlator, 4-point correlator, as a function of the cross ratios U, V, sigma, and tau, where U and V are the usual cross ratios of a conformal field theory, which are made out of the points x1, x2, x3, x4, and sigma and tau are very much the same, but for these are symmetry-wise null vectors that I introduced here. This function, because we have only a finite number of y's, it's just a polynomial in sigma and tau, while in U and V, it can be in principle a horrendous function of U and V. But in sigma and tau, it's just a finite order polynomial of order k, and that's all we have. So basically, the fact that we can write the 4-point function like this is the consequence of the bosonic part of the symmetry algebra, here and here. And we will see that the fermionic part of the symmetry group will also impose constraints, but I will talk about this later. Are there any questions?
So the Y part comes purely from the SO5 symmetry. The SO5
that's absolutely correct. So indeed, so it is convenient to introduce these null vectors, indeed. So they are just 4 null vectors, Y1, Y2, Y3, Y4, and the correlator depends also on these 4 null vectors. Yes. But it will be very convenient for us to do that, as you will see. So, great. So the structure that we expect now, as we consider these correlators in a 1/c expansion, is an structure which mimics the structure that we have in flat space. So we will have a disconnected part that will go like 1. Then we have a piece that corresponds to supergravity, to the supergravity approximation that is given by these 3-level diagrams. Then we will have a piece that corresponds to these contact diagrams that corresponds to this R⁴ vertex. And then we will have this sort of loop diagrams, etc., etc. But I would like to make two very important facts, in particular one very important fact. The 6D 2,0 theory is not a Lagrangian theory. So it's non-Lagrangian. So in particular, we have no weak coupling results. So in n=4 super-Yang-Mills, you have a ton of weak coupling results. And you can draw a lot of conclusions and inspiration from all these weak coupling results. We have nothing like that in the 6D 2,0. So we will try to work out for a theory where we have non-Lagrangian. Is that okay? So let's first look. So as I mentioned, so this is relatively trivial because it's just a disconnected contribution. So the first non-trivial part is what we denote is the 1/c piece, and is given by 3-level Witten diagrams, or is given by the correlator in the supergravity approximation. Okay? So the next 20 minutes of my talk will be about how to compute these 3-level diagrams here. So these diagrams at 3-level, at order 1/c. Is that okay? Any questions before I start?
I have a naive question.
Yes.
What is the loop counting parameter in these theories? Like
Yeah,
in string theory, we have GS, but how would I count the number of loops here in M theory?
Beautiful. So I will be much more clear later on. It is, but the only parameter we have is C. So the expansion will be an expansion in inverse powers of 1/c. But in principle, it also has fractional powers. So there is only C here.
No, so given a term in this perturbative expansion in 1/c with some fractional powers and integral powers, how do you determine whether it's coming from?
I will tell you. I will tell you later on. It will be a bit more clear later on, but yeah. So later on, it will be slightly more clear. But the thing is that in principle, so let me give you an answer right now, so you don't become too happy. Like if I give you the answer to order 1/c to the 20, you don't really know whether that answer came from one loop diagram or 2 loop diagrams or analytic diagrams. So in a way, in this problem in M theory, all the things mix together, okay?
Okay.
So 1/c is the only parameter you have, and that's all you have. Imagine that in a string theory, you've set alpha prime to be some value of C to some power. They all would mix together. So this is the situation here. But later I will be slightly more clear.
But in string theory, I still have GS, right? I can read up.
That's right. So yes. So here, that's right. So here there is a unique. So in a string theory, it depends whether you see the. So if you talk about a computation in n=4 super-Yang-Mills, you have 2 parameters. You have the central charge C, and you have lambda, the 't Hooft coupling.
Right.
Okay. Here you have only 1 parameter. So it's like many things that in n=4 would belong to different categories. Here, they all mix together because the only parameter you have is a 1/c.
Okay.
But this will be more clear later on. So let me give you a better answer when I have the ingredients to do that.
Fernando, what happened to the sigma tau dependence? Does that also come out?
Oh, absolutely. Yes, sorry. So just, yes, fantastic question. Sorry about that. So I was a bit lazy because it didn't fit on a single line, but indeed, but sigma and tau, so all these things depend also on sigma and tau. Sorry about that. So I shouldn't have suppressed this. So indeed, so sigma and tau is always there, and all these things will depend on sigma and tau as well. Yeah, sorry about that. I should have included sigma and tau here as well. So the dependence on sigma and tau should be understood, but yeah, I should have put it. So the first question we want to answer, and we will answer this in the next 20 minutes or so. Sorry if I go a little bit over time, but I love getting so many questions, so please keep asking. So we will try to understand how to compute this supergravity, this 1/c contribution here. And first of all, I should mention that there is a standard recipe to compute this 3-level contribution. So the standard recipe goes as follows. So first, you perform a Kaluza-Klein reduction of 11-dimensional supergravity on S4. And this gives you an effective action on ADS7 from where you can read off the cubic and quartic vertices. Once we have the cubic and quartic vertices, we can write down all the exchange and contact Witten diagrams that contribute for a given K1, K2, K3, K4, and then we just need to compute these exchange and contact Witten diagrams. And that's it, and we can go home. The problem with this approach, although this is a 3-level computation, there are several problems with this. So first, computing the effective action and extracting the vertices is extremely hard. This has only been done for the case of ADS5 cross S5, and even in that case, the answer takes 15 pages. There should be some field redefinition, and actually we have proven that there is such a field redefinition that makes the quartic vertices to disappear, but this is very hard to find. And another problem is that for general KI, the amount of Witten diagrams that you need to compute can be huge. And finally, the resulting Witten diagrams, even if you are able to write them down, they would be impossible to compute with the technology that we know. Okay? So because of all this, it is clear that this brute force way may not be the best way. But let me just let me show you this heroic attempt by Aryutunov and Frolov. So this is the kind of things that you get when you try to compute the effective action. And this is for the case of ADS5 cross S5, which should be much, much simpler than ADS7 cross S4, which no one did. Although, even though this method is a brute force, there is nothing wrong with it. And it's an honest way to do the computation. And actually, still many results were computed using this traditional method. But mostly, in the case of ADS5 cross S5, which is not exactly the case we are interested here. But for ADS5 cross S5, one can actually compute many things. So you can, for instance, compute 2222, 3333, 4444, and there was a conjecture for KKKK. Now, in the case of ADS7 cross S4, things are much harder, and this has only been done for 2222, and for the lowest, just for the stress tensor multiplet. And what happens is that for this particular correlator, one can forget about the S4 and all the Kaluza-Klein modes. And we can just consider gauge supergravity on ADS7. So the computation is much simpler, and Aryutunov and collaborators, Sokachev, I think, managed to do this computation for ADS7 cross S4, but just for this simple correlator 2222. While for ADS4 cross S7, there is actually nothing. So evaluating diagrams is much harder in this case. So this is the case we are interested in, but I will say what the results are also for ADS4 cross F7, which could be interesting. Now, the problem with this approach is that there is not a clear understanding of the underlying organizing principles of these amplitudes in ADS. There should be a better way. And a better way is to try to use a Mellin representation of this correlator in space-time. So the Mellin representation, given the correlator U and V on sigma and tau in space-time, we define a Mellin amplitude, which is a function of 3 Mellin variables, S, T, and U, and also sigma and tau. And here there is a product of gamma functions, which I am not writing down explicitly. And here S plus T plus U is equal to constant. I would like to add, recall that at the beginning of the talk, I told you that we should interpret the scattering amplitude on ADS7 cross S4 as a correlator of local operators in the boundary. But an apparent problem with this is that the amplitude depends on 3 Mandelstam variables, ST and U, while the correlator depends on 2 cross ratios, U and V. So the relation is not clear. But the solution is that it is this Mellin amplitude, the one that we should interpret as the M-theory amplitude on ADS7 cross S4. So this is the amplitude that we will be interested in computing. And through this transform is equivalent to the correlator of the 2,0 theory. Now, this function is a meromorphic function and has very nice properties. So it has crossing symmetry, which corresponds to exchange of ST and U with some reshuffling of sigma and tau. It also has a very nice structure of poles where exchange operators here in the S channel lead to simple poles with known residues of functions of U and T, the other 2 Mellin variables. And in addition, it is relatively easy to require the superconformal word identities. So I haven't spoken at all about the superconformal word identities. Recall that I told you that the fermionic part of the symmetry algebra also imposes some constraints on the amplitude. At the level of the Mellin amplitude, there is a complicated sheaf operator such that if you act with the complicated sheaf operator on the amplitude, that must be 0. So one is able to write down the superconformal word identities as some kind of complicated equation E equals like this, okay? So the Mellin amplitude satisfies all these properties. Crossing symmetry, the poles are defined in the structure of poles is very well understood. And in addition, it should satisfy these superconformal word identities. Is that okay? So,
so will the word
yes.
identity effectively determine the sigma tau dependence?
That's a very good question. I will tell you precisely. I will answer that precisely in a bit. The answer is no. The quick answer is no, but it determines some of it. So let me answer you in the next slide.
Thank you.
Right. So here is the answer, but let me go slowly. So an idea first implemented by Rastelli and Shaw is that rather than performing a direct computation, which as we have seen is very complicated, try to use these 3 consistency conditions to fix the answer. And it turns out that crossing symmetry, together with the structure of the poles, together with the superconformal word identities, has been shown in a case-by-case basis that in principle it fixes a unique answer. Now, in the case of ADS5 cross S5 and ADS7 cross S4, things are relatively nice because it turns out that one can solve the word identities. And we can write down the solution to this equation as follows. A solution to this equation takes always the following form, and it follows that the Mellin amplitude, the full Mellin amplitude, has to be equal to a given operator acting on a reduced amplitude, okay? So what we are saying is that the kernel of the superconformal word identities can always be written in this following form. And just to answer the question by Shiraz, so given the correlator of k, 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 the full amplitude is a polynomial of sigma and tau of degree k minus k, okay? While the reduced amplitude is a simpler amplitude, which is a polynomial on sigma and tau of degree k minus 2. And the rest is fixed by this operator here. Is that okay, Shiraz?
Okay, yes, thank you, thank you.
So I am saying that k minus 2 orders are not fixed by superconformal word identities. But in terms of, but then from k minus 2 to k is fixed by the superconformal word identity, okay? So what? Yes,
let me ask you just a vague question, which is probably so vague. Anyway, but let me ask it anyway. In terms of scattering amplitudes, you explained to us that all the polarizations were fixed in terms of just one scalar.
Yes.
And that felt to me like saying that your correlator should all be fixed in terms of just ST.
Beautiful question. Yes, I will answer that question precisely in a few slices. So I will answer that. I will answer that question in a bit. Okay.
Thank you.
Yeah, that's an excellent question. So I guess the question of Shira is, I told you that in flat space, all the polarization dependence was fixed. But here in ADS, I am telling you that that is not the case. And we will answer that question when we will analyze the flat space limit of our answers.
Fernando, are there any other solutions to word identity apart from this type of an exact one?
Say that again.
Are there any other solutions to the superconformal word identity apart from this one?
Yeah, that's a very good question. I think for ADS 5 cross S5, I don't think this is the case. But I think for ADS 4 cross, so in ADS 4 cross S7, things are much more complicated, and it is actually not known how to write down the full answer. So for three-level amplitudes, I think this is the only kind of solutions. However, to study mathematically this operator D is quite complicated. So it is not clear what the kernel of this is, and these are all non-invertible operators, etc. So I don't think it has been proven mathematically. However, what happens for ADS 5 cross S5 is that all the solutions can be written like this.
Okay.
Yeah, it's a very good question, actually. But let me, because I wanted to stress the fact, the following fact. So let me, in relation to what you say, let me say something in a bit. So it turns out that for ADS 5 cross S5, one can actually guess a general formula, and this has been done by Rastelli and so. But on the other hand, for ADS 7 cross S4, which is the case which is interesting for us, is much harder. And they have found only a few cases with low examples of these KIs. On the other hand, for ADS 4 cross S7, we don't know how to solve these word identities in general. So we don't have this kind of solutions. And actually, we will introduce a new ideas, and we will see that with these new ideas, this reduced amplitude doesn't play any role. So just to answer your question, in general, we have found that this is not very useful, and we will directly solve the word identities with this equation here. Okay?
Okay.
So, yeah, I don't want to stress too much the reduced amplitude because we don't use it. So, and I
Right.
am not sure it is
The
important.
fact that the solution can be written like that is just a coincidence, or is there a better understanding of that?
Well, no, for it, I mean, for ADS5, it is very nice because the structure in the reduced space is much simpler than the structure in the full space. Now, on the other hand, I think the amplitude, which is physically relevant, is the full one. So it is not clear what is the physical interpretation of the reduced amplitude. So it is the full amplitude, the amplitude that has a nice physical interpretation and the important one.
Okay.
Good. So we will try to introduce a new idea, since for ADS7 crosses 4 and ADS4 crosses 7, we don't know how to solve these things in general. And the new idea is actually the following. So the idea is to introduce the concept of maximal R-symmetry violating amplitudes. And recall that we consider this amplitude, these 4-point correlators. And these four-point correlators, each operator was labeled by a point in a space-time, x, together with a null vector in 5 dimensions. And recall that the way we introduced these 5-dimensional null vectors was by contracting these symmetric traceless operators with this null vector y. So now what we are going to do, we are going to choose a configuration where y1 and y3 are aligned. In other words, we will choose y1 and y3 to be such that y1 dot y3 is equal to 0. In terms of cross ratios, this is equivalent to setting the cross ratio sigma to 0 and the cross ratio tau to 1. So we are fully fixing the R-symmetry by saying that sigma is equal to 0 and tau is equal to 1, okay? And so just to answer the question to Shiraz, notice, Shiraz, that we are going to a specific R-symmetry polarization by choosing this, okay? So it turns out that this choice suppresses all exchanges in the U channel, and actually the amplitude simplifies drastically. And we define this MRV amplitude as the usual amplitude where sigma has been set to 0 and tau has been set to 1. And just to give you a flavor of the huge simplification, this is the stress tensor multiplet 4-point function, so it's just 2, 2, 2, 2 in ADS7 crosses 4. And it is given by this horrible polynomial of ST sigma and tau that I gave you here. But in the MRV limit, it is much, much simpler. And it's just given by this very neat expression of ST and U. And here there are two things that I would like you to notice. So the first thing is that the amplitude has no poles in the U channel. So we have poles in S, we have poles in T, but we don't have poles in the Mandelstam variable U, in the Mellin variable U. And the reason for that is that exchanges in the U channel are always proportional to y1 dot y3, but this is 0 in this MRV polarization. Another surprise is that this contains a double 0 in U, given here, and this can be understood as the fact that certain low twist double trace long operators decouple in this MRV configuration. And what is nice is that these properties are general. It's not only for the case at hand. So you get any amplitude, like 3333 or whatever, and you set them in the MRV limit, they always will have a double 0 and always will have no poles in U in this prefactor here. But it turns out, yeah, sorry.
And this discussion is for the exchange diagrams, right? But there are contact diagrams, and do they affect? I mean,
Beautiful.
They also affect?
Fantastic, excellent question. So absolutely correct. So here, so this is so what will happen. So let me put. So here, what we will do with this, we will fix the polar part of the Mellin amplitude, and then we will show that contact diagrams in the representation we will write are not present. And I would like to add something which is not very clear from what I wrote, but these super-conformal word identities, a nice feature of them is that once you fix the polar part of the Mellin amplitude, these super-conformal word identities would fix also the contact terms for you, okay?
So what is
so
the
like,
polar part?
Sorry?
Oh, you mean the pole? I see. Okay, fine.
Yeah, sorry, the poles, all the poles. Like once you fix all the poles, actually, by checking these super-conformal word identities, you can check whether these contact diagrams are there or not.
So this will fix also the sigma tau dependence.
Absolutely correct. Yes. So this is for all sigma tau. Yes.
Sorry, but the last thing you said confuses me, because it sounds like you're saying that if there are no pole terms, then there cannot be any contact terms.
Oh, right. Sorry. So there is. So yes. Sorry. So there is one. Yes, you are absolutely correct. So there is one more input that I need to give, and this input is the correct flat space limit. So the correct flat space limit will forbid this certain contact diagrams.
Okay, thank you.
Yeah, sorry. So that is important. So there are solutions that are just pure contacts, but these solutions will be forbidden in the flat space limit.
Sorry, Fernando. So are you saying that this computing amplitude in the MRV limit would fix the full amplitude using super-conform word identities and the flat space limit?
Yeah, it does, but let me go. You are basically, yeah, but let's not jump ahead of ourselves. Okay. So let me continue, and you will see. So as I just mentioned here, we have this drastic simplification in the MRV limit. In particular, we have these double zeros and this absence of poles in the U channel. And what happens is that these properties are actually highly non-trivial at the level of exchange Witten diagrams. And what happens is that in this MRV limit, if you require these two properties, all cubic couplings are fixed in terms of scalar couplings. And actually, once you have realized that, you can write down the general MRV amplitude for all K1, K2, K3, K4. And just to answer your question, indeed, our symmetry can now be used to restore the full sigma and tau dependence of the full amplitude. So the answer to your question is yes. In principle, there could be contact terms here, and I will mention this in a little bit. But indeed, what happens is that we can use this R-symmetry to restore the full sigma tau dependence. So what we are left with is the full amplitude for all K1, K2, K3, K4 with the full sigma and tau dependence, okay? So the solution takes this form. So it's a sum of S channel plus T channel plus U channel. Sorry, this plus should not be here. Where each of the channels is a sum over poles, and we have a completely closed form expression for what the residue of the poles is. And this gives a compact and explicit expression for the full 3-level amplitudes for all K1, K2, K3, K4. Actually, the same strategy also works for ADS5 cross S5, and we can finally prove the answer by Rastelli and so, but also for ADS4 cross S7. So this gives all the holographic correlators for generic K1, K2, K3, K4 for all maximally supersymmetric theories in dimensions higher than 2. And let me mention something that I didn't mention before. So as we discussed before, in principle here, you could put some contact terms. You could add some extra contact terms. But what happens is that you can check explicitly that the word identities are satisfied and the flat space limit works, and any contact term that you add would actually spoil these properties. So once you get the answer, you can check the word identities and the flat space limit, and that tells you that contact terms are actually not there, okay? So they are actually absent. So are there any questions?
Fernando, just to clarify, this absence of contact terms is not a statement about some property that arises because of Regge boundedness.
Well, so here, right? So there are two. There are different kind of. So here, so what happens? I didn't write the details, but what happens is that you have many exchange diagrams in ADS for the Witten diagrams you need to compute, and each of these exchange diagrams would in principle have this regular contribution here. But we have managed to write the answer in such a way that, right, however, as I mentioned before, once you act with these superconformal word identities on a given multiplet, this will fix this regular term multiplet by multiplet, okay? And we have checked that in the final answer, if you act with superconformal word identities, the superconformal word identities are satisfied without adding any contact term here. Then you can ask whether I could still add some contact term that satisfies these word identities, etc. And what happens is that this would violate the flat space limit that I will explain in a second. Okay?
Yeah, okay. Thank you.
You're welcome.
You also give some intuition as to why this MRV limit is so special in that it parameterizes in some sense the solutions of the word identity.
Yeah, I mean, we don't know. We were playing with other limits. And actually, I must say that there are three similar MRV limits. So there is a limit where you can align Y1 with Y2, Y1 with Y3, and YY with Y4. And this limit, they seem to be special limits. But what is important, I think to me, what is surprising is this one here, is the fact that R symmetry can be used to restore the full sigma tau dependence. And the reason for that is that if you see at the R symmetry polynomials, which are some polynomials that depend on the representation of exchange operators and depend on sigma and tau, what happens is that all of them survived in this MRV limit. Mm-hmm. So although you are killing a lot of terms, all the R symmetry polynomials actually survive in this limit. And because of that, because they survive, you can fix the coefficient in front of all of them, and then you can write back the full sigma tau dependence.
I see.
So I think that is a nice property that you could, of course, say, okay, why not sigma equals 0 and tau equals 0, or something like that. But not all the R symmetry polynomials would survive in that limit. So this I think is a nice property. So and let me mention something also to answer the question by Shiraz about the polarization and the sigma and tau dependence. It is actually interesting to consider the flat space limit of the answer we have gotten. And what happens, so here the large ST and U limit, the flat space limit is a limit where you take ST and U to be very large. And what you can prove is that in this limit, everything has this form here. And this is, so I have forgotten, so let me tell you the structure. So first you see a 1 over STU, then you see some function of ST and U, and also sigma and tau, which is a degree 2 polynomial. And also you can find a degree k minus 2 polynomial, which is completely fixed in the flat space limit, okay? And this structure here should be compared with the 11-dimensional 4-point amplitude now for an appropriate polarization. And remember that I told you that the 11-dimensional amplitude was equal to this k hat factor divided STU, and actually one can show that in the correct polarization, which is p dot theta equals 0, this k reduces precisely to this factor that we see here. So to answer the question of Shiraz, although the sigma and tau dependence is very complicated, in the flat space limit, the dependence is fully fixed and it agrees with what you would expect from the 11D computation. Does that answer the question?
Yes, it answers. So the terms that are not fixed disappear in the flat space limit.
That's correct. So that they are complicated, but they have like 1 over S correct, like 1 over ST and U corrections with in the limit. That's absolutely correct. Yes.
Okay, thank you.
You're welcome. Good. So this is basically the story I wanted to say at 3 level. I don't know how much longer can I take. Sorry, I don't know about the times.
How long do you think you would need?
Maybe like 10 minutes.
Sure. Yeah.
Yeah, sorry about that. So I wanted to tell you the story about the loops.
Sorry, I can ask a question before that. So in this case, let's say you fix the MRV amplitude, then how easy or difficult is it to recover the entire amplitude?
It's not difficult at all. Like if you write the full amplitude, well, it depends how you write it down. If you write the full amplitude in terms of some linear combination of these R-symmetry polynomials, what happens is that the coefficients in front of the R-symmetry polynomials are completely fixed. And once you realize that, you can just reintroduce the full sigma and tau dependence.
Okay.
Of course, if you had just the full amplitude to guess, it would be extremely hard to guess. And just for people like who likes hypergeometric functions, I can tell you, it is possible to do these sums, and the kind of functions you get are 8F7 hypergeometric functions.
Wow. Okay.
So the function is complicated, but if you write it in the right way, you do have a compact expression. And for any K1, K2, K3, K4, we have written a mathematical code. It gives you the answer in 1 second. So you can choose any K1, K2, K3, K4, shift enter, and you get the answer.
Thank you.
Sorry, I missed something elementary. Could you go back last?
Yes, of course.
Yes. You said all cubic couplings are fixed in terms of the scalar coupling.
Yes.
Where did you get that from, please?
Yeah, sorry. So basically, you can consider it. So sorry, I didn't write down the answer here. But basically, when you exchange Witten diagrams, you have many exchange Witten diagrams, let's say here, And you have all the fields that are exchanged. And you have scalar fields, you have spin 1 fields, you have fermions, you have spin 2 fields, etc. And you have many components in the multiplets that you exchange in the supergravity computation, okay? And in principle, all of these have different cubic couplings. So you need to, so here, maybe here. So here, you have to sum overall exchange Witten diagrams, but the intermediate fields here, they can have a spin 0, a spin 1, a spin 2, okay? And they are all the fields that you can exchange in 11-dimensional supergravity multiplet, okay?
Yes, yes.
And what happens is that if multiplet by multiplet, you require that in the MRV limit, this happens, this structure of double zeros, etc., you get an equation that relates all cubic couplings in terms of the scalar couplings only. But this is great, actually, because what happens in ADS 7 x S4 is that all the other couplings were not known. So people didn't know what, for instance, even if you want to write down, let's say, this Witten diagram here, and you are exchanging a field of a spin 2, you need to know what the cubic coupling is, okay?
Okay, yes.
And what happens is that, yeah, this fixes, this requirement in the MRV limit fixes all the couplings just in terms of the cubic coupling. And in addition, we have found a way where these contact diagrams are not there. Yes, sorry.
So the key physical input seemed to be that you had, that the fact that there were these double zeros had a lot of content.
That's right. And actually, in retrospective, it is not more content than the one hidden in the super-conformal word identities. But it is much, much easier to impose. You can also take multiplet by multiplet. You could act with the super-conformal word identities, and also that would give you a relation between the cubic couplings. But the point is that that is very hard to do. It's very hard to implement.
Okay, thank you.
While these double zeros are very powerful, so they are very simple to implement. And then we have found a way where contact diagrams are not there, and that's just luck, I think.
Thank you.
Great. So then let me before going quickly to loops, let me say you quickly that we have also contact diagrams. So this corresponds to the next, to this R to the 4 term. And I don't want to spend too much time on them, but it happens that in Mellin space, the solution is simply a polynomial. And for the case 2kk, that is the case that will be interesting for us, they are actually fixed by consistency conditions up to an overall constant. And this corresponds to the contact term, R to the 4, and this overall constant can be fixed by taking the flat space limit and mapping to the known answer. I don't want to spend too much time on this, but this is, so we know what the answer is. It's much simpler than Sugra. It's just a polynomial in Mellin space. So the next one are loops. And here, sorry, I will go quickly, but ask me questions if you have any questions. But this, it turns out that this can again be fixed by consistency conditions, but here, purely conformal field theory ideas, as opposed to Witten diagrams in ADS kind of ideas, seem to be more powerful. And the consistency conditions here are crossing symmetry, conformal partial wave decomposition, plus the CFT data at the previous order, and the analytic structure for complex cross ratios. I had a slide explaining how this works, but it's a bit technical, so let me skip this. But at the end of the day, what happens is that at loop order, the solution is, in a very precise way, the square of the solutions at previous order. So for instance, remember that I told you that the gravity solution corresponds to exchange diagram like this, and the vertex solution, this contact term corresponds to this one. Then, for instance, the first loop, you cut it into two and corresponds to the square of two gravity solutions, like here and here. So what we are doing, and this can be done also in formulas, we are implementing the unitarity methods in ADS. And the same is true for all other vertices. For instance, you get this loop diagram by putting together two tree levels like this. So this is of order C to the -2, but we have other diagrams where we put together this and this. So this will be of order C to the -8/3. So this is the structure. I got a question today on what is the structure in a 1/C expansion. So this is the structure in a 1/C expansion, okay? And each loop, you can cut it and you can produce it from putting together these tree-level diagrams. Is that okay?
Sorry, as you said earlier in the talk, this should only work up to polynomial ambiguities at the appropriate order.
Absolutely correct. So
and you
indeed,
now how to fix those.
Fully. No, I won't.
Okay.
Sorry. Yeah. No. But I will mention this. Yes, that's absolutely correct. So, for instance, here C -2 in principle. Here you can have this kind of terms. So, yeah. So let me mention that in the discussion. But indeed, I mean, we will be able to fix something that is the same that you are able to fix from some unitarity method in flat space. But here we are doing some unitarity method in ADS. So let me, okay, just one little word of caution is that here one will have some kind of mixing problem to solve. And basically the point is that whenever you cut, let's say this loop diagram in the middle, you will get these two tree-level diagrams. But of course, the point is that all these Kaluza-Klein modes can also run along this loop, and they will run along the loop. So even if you choose to study the correlator 2, 2, 2, 2, along the loop, generic Kaluza-Klein mode can run. So it means that at tree level, you will need to study 2, 2 pp. And that's the reason why the tree-level correlator 2, 2, 2, 2 is not enough if you want to study loops. Because for loops, you need tree-level diagrams, but also tree-level diagrams like this one here, 2, 2 pp. Is that clear? Then let me tell you what the structure of the answer is. So in Meline space, this function M corresponding to loop Sugra corresponds is a meromorphic function with double poles. After like 3 months of computation, we can guess the analytic form of these residues here. The analytic form is like this. And this is an example, I think the first one, of a quantum M-theory amplitude on ADS. And it's, as far as we are aware, the first quantum correction for a non-Lagrangian theory. So this is the answer of the holographic 2, 2, 2, 2 correlator to order 1/C squared, or 1/n to the 6. Let me mention let me mention about the flat space limit. Now the flat space limit is you have to take S and T large, but it's a bit non-trivial because there are these sums over M and N. And what you can show is that the limit to study, so it's like a saddle point, you need to study S, T, M, and N, or large at the same rate. And the final answer takes this form here, where M and N, they have been converted from a sum to an integral. And this exactly agrees with the 11-dimensional box integral. So we have done a computation in the 2,0, in the 6D 2,0 theory. We now take the flat space limit and we recover precisely the answer that we expect, which is the answer for loop M theory in flat space. Is that okay? So let me conclude. I'm sorry for going over time. So also I would like to conclude with some discussion. So we have developed a powerful method to compute holographic correlators dual to ADS 3 amplitudes. And this also works for all maximally supersymmetric backgrounds. We have also developed a method to compute 1/c squared correlators in the 6-dimensional 2,0 theory. And this is the first loop computation in a non-Lagrangian theory. And from this one, so one interesting thing that you can obtain, like you can tell me, what do you do with this sort of answer, right? Like, so what? So one thing that you can obtain now is a wealth of CFT data about this theory. So for instance, this is the anomalous dimension of the leading twist operator with a spin 4. And we know that this anomalous dimension in a 1/c expansion starts with 12, now has a 1/c, and now has a 1/c squared, and so on. So just to answer Shira's question about ambiguities, it is true that we will have ambiguities when we do, let's say, this computation here, but these ambiguities will not modify the anomalous dimension of higher twist operators. So the ambiguities only will give, so they correspond to contact diagrams, so they will only give anomalous dimensions to operators up to a given twist. But then the reason why I have written this operator with twist 4, with spin 4, sorry, is because of the following. So the 6-dimensional 2,0 theory gives actually a non-perturbative definition of M theory, at least on ADS7 x S4. So now we can, using this perspective, we can try to use bootstrap to answer questions about M theory. And a target question is whether this term D8 R to the 4 is present or not in the effective action. And for this, there is a very good idea, because for that, the only thing that we have to do is we have to measure this delta 4. So if the numerical bootstrap was super precise, and we could measure this delta 4 for very large values of the central charge, we can try to do a 1/c expansion. And in the next order here, we would see, by computing that, we can see whether this term is present or not in the effective action. And this will be something that the bootstrap can teach you about M theory. So this term here. And in particular, what we have proven is that we can compute all the previous terms in a 1/c expansion. So the next one will depend on this coefficient and known coefficient gamma. So thank you so much.
Let's all unmute and thank Fernando. Questions?
Hi, Fernando. I have again a vague question.
Yes.
Your method, as you explained, has basically all the ambiguities of the amplitude program, in the sense
Yes.
that as you go higher and higher order, there would be an infinite number of constants that you would have to keep fixing, right, at each
Yes.
order level.
Yes.
I was wondering whether the fact that you've got some well-defined CFT, whether there's some hope for an in-principle way of fixing these ambiguities.
Yeah, I think so. I think so. So I think the point is that in order to do an analytic computation, I am doing, of course, I want to get analytics because I like analytic numbers. And what I am doing is a 1/c expansion. Now, in a program like in the numerical bootstrap, the numerical bootstrap would be valid for finite C. So I think what the dream, so what actually one would expect, hope, is that if you do the numerical bootstrap for finite C, there will be theories. So there will be some region that is allowed region and some forbidden region. And interesting theories would live at the boundary of this region. So at the boundary of this region, you can expect to have some methods that can allow you to compute what's going on. So I think yes, but one will have to take into account the fact that C, to do things non-perturbatively in C. And that may be extremely hard, but in principle, that is the idea.
And just a quick follow-up, Penedonnes and Gibodev, and then this paper, which I'm not sure has yet come out, by Rastelli and Mazak and various people, other people, Simons Duffin. There's this idea of this, some sort of non-perturbative functional, which could be.
Yeah, I mean, what happens in some, so I think that would be great. And if the point is that, of course, one has to see, to prove, is that the theories we are interested in live at the boundary of these exclusion regions. And yeah, so that would be very nice to see if it works. So in principle, it can work. So one of the problems with some of the original papers on these functionals was that they were assuming, they usually assume non-degeneracy, and this assumption is just not valid in a 1/C expansion.
Thank you.
So one will have to see if this assumption. Also, I was talking to Sasha Shibuevo, that they were trying to use their paper with Penedonnes to work in the epsilon expansion. But the problem was that at some point you have this degeneracy, which kicks in. And that's a problem in whatever thing you do. But in principle, yeah, like one may hope to kind of overcome that problem. That would be great, of course.
So, I have a slightly tangential question. Shinan, I think, had a paper about imposing word identities in Mellin space and so on. So how does this, is this complementary, or I mean, does this method do precisely the same thing that that would do? How does it relate to that?
Yeah, so for us, we need to impose the word identities. And I think the point is that there are two ways to do them. And one is just, you work with solutions like this, right? And but in one of his papers, that was the thing we most closely follow, you work at the level of word identities written like this.
Right.
And so he wrote the most important one. There is another, so it's like the word identity is split into two. In his paper, he considered one of them. In this new paper, we consider both of them. But indeed, we see that the word identities indeed are satisfied. But yeah, it's very similar to the things he was doing. So they are word identities in Mellin space, and you look directly at this equation rather than just trying to write a solution.
Right. So, and in this MRV amplitude, is this supposed to parameterize the solutions again, just like the reduced amplitude? Sorry, I'm going back a little bit. I just want to understand the what role.
Yeah, of course. Yeah, it doesn't seem to be very helpful to. So we try to study the reduced amplitude in this MRV limit. It doesn't seem very useful. Also, it has to be said that when you take this operator D, this operator D takes derivatives with respect to sigma and tau. So you are not allowed to set sigma and tau to 0 and 1 and then take this operator D. So it's a bit complicated. So this MRV seems to make more sense at the level of the full amplitude.
Okay. Any more questions?
I have a very naive question. So So you talked about these three examples that's there on the slides: ADS5 cross S5, ADS7, S4, ADS4, S7.
Yes.
Let's talk about ADS3 times S3 times T4, for example. In the
Yeah, that's a bit different, and I am not doing that because I am doing, sorry, dimensions higher than 2.
Okay.
Yeah, but that would be very interesting actually. But
there we do know how to write the string action, right? I mean, most from the string theory side, we do know more than.
Yeah. So on the other hand, the structure of the word identities is a bit different there.
Okay.
Yeah, but it's like you have half of them, and it's a bit different. I'm not saying that it cannot be done, but it's a bit different.
Okay.
Yeah.
Okay, if there are no further questions, let's thank Fernando for a wonderful and extremely clear talk.
Thank you so much.
It was totally great. And I mean, it was really wonderful, very clear. Thank you so much.
Thank you so much. Thank you. Thank you. That's very kind. Okay, thank you so much for everything. Keep safe.
Thank you.
Thank you. Bye.